So now we want to remove the sample. And to do that, the first thing we want to do is tank vent. So what you are trying to do is to release the vacuum in the chamber. When you press tank vent, the vacuum pump does that automatically. But to speed this up, I'll just open this. So we're releasing the vacuum. Then after that, what we do now is to open the chamber. You press door release on the console, and now you can remove. So now we're going to move the wedge back so that we can remove the sample. And to do that, you press run mechanical on the console and allow the pressure to build up. And after it has built up, then what you need to do is to move the wedge. And you can see as the wedge moves backwards. It's not moving by itself. I am the one actually moving it. So now I can then do stop. Because I can't put my hand there while you have the run mechanical lights on. So I'm going to remove the sample. So it's like the sample is stuck. So I need to find a way to remove it. This you should expect. Okay, let's remove the sample. So I said I was going to make you a coin. Now I've made the coin from the initial sample that we had there. So now we can carry out further studies by sectioning this sample into two, mounting it, and then observing the microstructure of this deformed sample. And the microstructure would give us an idea of the defects that might be present as a result of the deformation. It will also give us information about the mechanisms controlling the deformation. All this information we need to be able to shape metals into different profiles as we have them for different engineering applications. So that's the end of the flow stress test. But one more interesting thing to show you would be the results. How do we know if we've achieved what we wanted to achieve? We need to check on the computer. And I will show you a quick check that you need to do on the computer so that you can be sure whether to accept the result or to repeat the experiment. Also, you can also check by calculating what is called barreling coefficient. You need to check the Gleeble application notes on how to do that. For every sample, you need to calculate the barreling coefficient, and that requires you measuring the diameter of this deformed sample, and of course, the final height. So the instruction on how to do that will be found in the Gleeble application notes. But how you can do a quick check on the computer, that's the next thing that I'm going to check, that I'm going to show you. Now we need to check the results obtained. We need to know if the Gleeble actually did what we asked it to do. So the result acquired is always captured in a software called Origin. So for you to analyze the result, you need Origin software. So this is a customized one as it has Gleeble as one of its tabs, but you don't really need that to plot your graphs anyway. The reason why you have it here is to simplify how you plot the graphs. So to check whether Gleeble did what we expected, we have to find the strain rate. So how do you do that? What we need to do is we can maximize and then highlight strain. Then you can click on plot. Then you select line and you have that. So we can now further analyze this graph. So I'm going to minimize this so that you have this. So you see we've plotted strain, the highlighted one, against time, and that gives you the strain rate. So we're going to analyze this and calculate the slope of this line you see here. The slope will give us an idea of the strain rate. And how do we do that? I would first maximize this a bit by picking a magnifying lens and then magnify. Once I do that, then I can select data selector, and then I can calculate the slope of this line, because this is the period when we were carrying out deformation. Prior to that, we were only holding, and there was really no strain. So here, we can now select from one end to the other. Then you go to analysis. From analysis, you go to signal. No, not signal. You go to fitting. When you go to fitting, you go to linear fit, then you select last used. And here you see the slope. The slope is 0.10028. And if you look at the error margin, it's very, very small, which means that the strain rate that we have obtained is the strain rate that we have asked the machine to do. And that's the strain rate of 0.1. The negative sign that you've seen there only signify compression. If we had done the test under tension, then it will be positive sign. But don't forget that the flow stress measurement is obtained from uniaxial compression testing. So here, you would find out in some cases that you don't achieve this strain rate. That means you have to repeat the experiment and you have to make some adjustments when computing your parameters on the QuickSim software. So this is the quick check that you would always do to ensure that the Gleeble had done what you want it to do. So another thing that you can do is to plot the stress strain curve. To plot the stress strain curve, you can click on Gleeble, then you select Gleeble graphs and you check the stress strain curve, and you have the stress strain curve. And you can see the stress strain curve here. It's already showing you the trends. So you can actually see the behavior of this material under compression. At that temperature, we have initial increase in flow stress, then you reach a peak before softening takes over, and you see continuous flow softening until the final strain was obtained. And like it showed on the machine, on the console, that we couldn't achieve the strain of 1.0, we did achieve 0.98, which is close to 1. But if you really want to achieve 1.00, you need to repeat the experiment and tweak your parameters a bit. Like I said, the negative sign you're seeing here is just indicating that we're carrying out compression. But you can always convert this to positive. And this is the flow stress and this is the strain. We can make this a little bit neater by adjusting the X and Y axis, that is the stress strain axis. So here I'm going to start from 0 and I'm going to keep this as negative 1.0, and then you click on apply, And on the vertical side, I'm going to go in compression by 20, and I'm going to click apply, and I think I need to go a bit more, 25, apply, and that's it. So so you see it's much more neater. And yeah, so that comes to the end of the whole analysis. I've been able to show you how to determine the strain rate, and by plotting strain versus time, and you calculate the slope of this deformation region, that is strain per unit time, and the slope tells you the strain rate. And again, this is the stress strain curve indicating the flow stress. The acquisition rate was quite high, and that's the more reason why you see all this noise. If I had reduced it to maybe 200, maybe it would be better. But this you can always fine-tune using the Origin software. You can clean it up and make sure that you don't overdress the data so that you don't lose significant information. So that comes to the end of this experiment, and of course the end of the analysis. So thank you.